Hi everyone, welcome back to Electrical Engineering 1. This is your lecturer John, and this time we'll be going to Chapter 3, Methods of Analysis. Remember that last time we have talked about Ohm's Law and Kirchhoff's Law. This time we are going to apply this in circuit analysis. We will be talking about two techniques. One is nodal analysis, which is based on Kirchhoff's current law or KCL. The other one will be mesh analysis, which is based on Kirchhoff's voltage law or KVL. Take note that any linear circuit can be analyzed using these two techniques. Part 1. Let us start with mesh analysis. Remember that in mesh analysis, we will be using mesh currents as the circuit variables. And we will be using KVL to find unknown currents. There are 3 steps to follow in mesh analysis. The first one is to identify the loops, and we are going to assign mesh currents to these meshes. Next, we are going to apply Kirchhoff's voltage law to each of these mesh current. And with the resulting simultaneous equations, we will try to solve for the mesh currents using any mathematical techniques. To fully understand mesh analysis, let's go to this example. In this circuit, there are 2 meshes. They are labeled as A, B, E, F, A, and the second one will be B, C, D, E, B. After identifying the meshes, let us now assign the mesh currents to these 2. For mesh A, B, E, F, A, let us assign mesh current I1. For the mesh B, C, D, E, B, let us assign the mesh current I2. We also need to assume the direction of these currents. The direction of these currents will affect the equation that we will be able to derive later on. In this example, we assume that the mesh current I1 flows in a clockwise direction. Same thing with the mesh current I2. Let us now apply KVL to these 2 meshes. Take note of resistor R1. The current through R1 is the mesh current I1. Going to resistor R2, the current through R2 is the mesh current I2. But if you go to resistor I3, there are 2 currents flowing through it, I1 and I2. This we have to consider in creating the KVL equations. And again, we should remember that current will always enter the positive side of a resistor. So now, let us go to mesh 1. What is the equation that can be derived from mesh 1? Following in the clockwise direction, starting from the voltage source V1, we have negative V1 plus R1 multiplied by the current I1 plus R3 multiplied by I1 minus I2, and this is equal to 0. Remember KVL, the summation of voltage in a complete loop is equal to 0. Now why is it that V1 is negative and then the voltage drop across R1 is positive and the voltage drop across R3 is positive? Since I have said earlier that current will enter the positive side of a resistor. The positive side of the resistor is connected to the positive side of the voltage source V1. Thus, they are subtracted. Rearranging the variables, we can come up with the quantity R1 plus R3 multiplied by I1 minus R2 multiplied by I2, and this is equal to V1. Let us label this as equation 1. Now, let us go to mesh 2. Following the same method as we have done in mesh 1, the equation that we can derive in mesh 2 will be R2 multiplied by the current I2 plus V2 plus R3 multiplied by the quantity I2 minus I1, and this will be equal to 0. Now, you might ask, why is it that in mesh 2, all the voltage drops are positive? Take note on the circuit, current enters the positive side. Thus, the negative side of the resistor is connected to the positive side of the voltage source. Thus, they are additive. Simplifying the equation that we derive, we can now rewrite it as negative R3 multiplied by I1 plus the quantity R2 plus R3 multiplied by I2, and that is equal to negative V2. Let us call this equation 2. Now, for these two equations, we know the values of R1, R2, R3, V1, and V2. The only unknown variables then will be I1 and I2. We have two equations, we have two unknowns. We can solve it by simultaneous equations. Part 2. This time, let us go to nodal analysis. If in mesh analysis, we consider the current through each loop, in nodal analysis, we consider the voltage in each node. Which means that given a circuit with n number of nodes, then we can accomplish nodal analysis by applying KCL to each node and applying simultaneous equations to obtain the unknown voltage. Knowing the unknown voltage will enable us then to determine the current in each element. Let us see now how we are going to apply nodal analysis in this given circuit. This given circuit basically has three nodes. They are labeled in these circuits as node 1, node 2, and node 0. Node 0 will be considered as the reference node. We then assign voltages on nodes 1 and 2. In node 1, we can designate the voltage as V1, and in node 2, we designate the voltage as V2. We then assume the current in each element from each node. Let us consider node 1. There are two constant current sources attached to node 1. One is IA, which is going into node 1, and the other one is IB, which is going away from node 1. We then assume the currents through R1 and R2. We assume that the current through R1, which is I1, is going away from node 1, and the current through R2, which is I2, is going away from the node. We then apply KCL in node 1. Remember, in KCL, current entering the node is equal to the current leaving the node. In node 1, current IA is entering the node, and currents IB, I1, and I2 are leaving the node. At node 1 then, the equation that we can obtain will be IA is equal to IB plus I1 plus I2. Now, let us go to node 2. In node 2, there are three branches. One is the constant current source IB, which is now directed towards the node. The resistor R2, whose current I2 is now also directed towards the node. And then the resistor R3. We assume that the current through R3 will be I3, and we can assume that the current through R3 will be directed away from the node. Applying KCL now to node 2, we can say now that current entering is equal to current leaving, which means that IB plus I2 is equal to I3. We now apply Ohm's law to find the currents I1 and I2 and write them in terms of voltages V1 and V2. The current I1 is equal to V1 divided by R1. I2 is equal then to V1 minus V2 divided by R2. I3 then is equal to V2 divided by R3. To simplify the equations, we can then represent the resistances in terms of conductances G, which means that conductance G is equal to 1 divided by R. Thus, we can say that I1 is equal to G1 multiplied by V1. I2 is equal to G2 multiplied by the quantity V1 minus V2. I3 is equal to G3 multiplied by V2. We then substitute this into the node equation that we have obtained. Thus, IA is equal to IB plus G1 multiplied by V1 plus G2 multiplied by the quantity V1 minus V2. Also, we can say that IB plus G2 multiplied by the quantity V1 minus V2 is equal to G3 multiplied by V2. The two unknowns now are just V1 and V2. Applying the method of simultaneous equations, we will then be able to solve for V1 and V2 and solve for the currents I1, I2, and I3. We now have two analyses, mesh and nodal analysis. When then can we use nodal analysis? We can use nodal analysis if 1. The network has many parallel connected elements. Second, if the network has current sources. Third, if the network has supernodes. And fourth, if the network has fewer nodes than meshes. Thank you and have a great day. Remember, work hard, work smart, and work your way to your dreams.